Nodes. In Kubernetes, nodes are the individual machines that form the cluster's infrastructure, responsible for running applications packaged in containers. They consist of components such as the kubelet, container runtime, and network plugin. Each node has a unique identifier and IP address within the cluster. Nodes facilitate workload distribution and resource management, ensuring efficient utilization of cluster resources. Kubernetes nodes are scalable and can be grouped into zones or regions for fault tolerance and high availability. Two main ways to have nodes added to the API server. In Kubernetes, nodes can be added to the cluster dynamically through self-registration or manually by administrators. 1. Self-registration. Nodes autonomously register with the Kubernetes API server, simplifying the process of adding nodes to the cluster without manual intervention. 2. Manual administration. Alternatively, administrators can manually add nodes to the Kubernetes cluster, providing greater control over configuration and management, which can be useful for specific deployment scenarios or infrastructure maintenance. These methods offer flexibility in node management, allowing for dynamic scaling and fine-grained control over the cluster's infrastructure. Node name uniqueness. In Kubernetes, each node in the cluster must have a unique name to avoid conflicts and ensure proper identification and management within the system. 1. Identification. Node names serve as unique identifiers for individual machines in the Kubernetes cluster. 2. Preventing conflicts. Ensuring node name uniqueness prevents issues such as misidentification, scheduling errors, and resource allocation conflicts. 3. Cluster consistency. Unique node names contribute to maintaining a consistent and reliable cluster state, enhancing cluster management and operation. 4. Administration. Node name uniqueness simplifies administrative tasks such as troubleshooting, monitoring, and applying configuration changes to specific nodes. 5. Enforcement. Kubernetes enforces node name uniqueness as a best practice, promoting reliability and stability in cluster operations. Self-registration of nodes. In Kubernetes, self-registration enables nodes to autonomously join the cluster without manual intervention by administrators. 1. Automated process. Nodes register themselves with the Kubernetes API server upon startup, streamlining the process of adding new nodes to the cluster. 2. Dynamic scalability. Self-registration allows the cluster to scale dynamically in response to workload demands, without requiring manual intervention for node addition. 3. Simplicity. By eliminating the need for manual node administration, self-registration simplifies cluster management and reduces administrative overhead. 4. Flexibility. Nodes can join the cluster from various environments, such as on-premises or cloud-based, facilitating hybrid and multi-cloud deployments. 5. Resilience. Self-registration enhances cluster resilience by enabling nodes to rejoin the cluster automatically after temporary disconnections or failures, improving overall system reliability. Manual node administration. In Kubernetes, manual node administration involves adding nodes to the cluster through direct intervention by administrators. 1. Administrator control. Manual node administration allows administrators to have precise control over node configuration, networking, and resource allocation. 2. Customization. Administrators can tailor node settings to meet specific requirements, such as assigning labels, taints, or custom configurations. 3. Security. Manual node administration enables administrators to enforce security policies and access controls, ensuring the integrity and confidentiality of the cluster. 4. Auditability. By manually adding nodes, administrators can maintain detailed records of node additions and changes, enhancing auditability and compliance. 5. Complexity. While offering granular control, manual node administration can be more complex and time-consuming compared to automated methods like self-registration, particularly in large-scale deployments. In Kubernetes, node status reflects the current operational state of a node within the cluster. It provides vital information for cluster management and monitoring. The node status includes readiness, conditions, and resource availability. When a node is ready, it indicates that it's operational and capable of accepting pods. Conditions such as network connectivity, disk pressure, and memory pressure offer insights into the node's health. Node status is continuously updated based on heartbeats sent by nodes to the control plane. These heartbeats ensure real-time updates on node health and availability. Monitoring node status helps administrators detect issues promptly and take corrective actions to maintain cluster stability and performance. Ultimately, node status plays a crucial role in orchestrating containerized workloads and ensuring optimal resource utilization within the Kubernetes cluster. Node heartbeats. 1. In Kubernetes, node heartbeats are periodic signals sent by nodes to the control plane. 2. They provide real-time updates on node health, including readiness and resource availability. 3. Heartbeats ensure continuous monitoring of node status, helping detect failures or disruptions promptly. 4. The control plane uses these heartbeats to maintain an accurate view of cluster health and availability. 5. Node heartbeats are crucial for orchestrating containerized workloads and ensuring high availability within the Kubernetes environment. Node controller. The node controller is a core component of the Kubernetes control plane. It manages the lifecycle of nodes within the cluster, handling tasks such as addition, removal, and reconciliation. The node controller ensures nodes operate within resource constraints and handles node-related events. It monitors node health and readiness, taking actions to maintain cluster stability. The node controller plays a crucial role in orchestrating the dynamic scaling and resilience of Kubernetes clusters. Rate limits on eviction. Rate limits on eviction in Kubernetes prevent excessive disruptions during node maintenance or failures. They regulate the pace at which pods are evicted from a node, minimizing impact on running workloads. Eviction rate limits help maintain cluster stability and performance during resource-intensive operations. Kubernetes applies these limits to ensure smooth operation and prevent overload on cluster resources. Rate limits on eviction contribute to the reliability and resilience of Kubernetes clusters by managing workload migrations effectively. Resource capacity tracking. Resource capacity tracking in Kubernetes monitors CPU, memory, and other resources on nodes. It provides real-time insights into resource utilization, enabling efficient workload placement. Kubernetes tracks resource usage to ensure optimal allocation and scaling of applications. Capacity tracking helps prevent resource contention and performance degradation within the cluster. By maintaining awareness of resource availability, Kubernetes optimizes resource utilization and enhances cluster efficiency. Node topology. Node topology in Kubernetes refers to the arrangement and relationships between nodes within the cluster. It includes factors like geographic location, availability zones, and network connectivity. Node topology helps optimize workload placement for performance, resilience, and compliance requirements. Kubernetes uses node topology information to ensure high availability and fault tolerance. Understanding node topology is essential for deploying applications strategically and maximizing resource utilization within the cluster. Graceful node shutdown. Graceful node shutdown in Kubernetes involves gracefully terminating running workloads before shutting down a node. It ensures that pods are gracefully evicted, allowing them to complete ongoing tasks and gracefully terminate connections. Graceful node shutdown prevents service disruptions and data loss by ensuring orderly workload migration. Kubernetes controllers coordinate the shutdown process, rescheduling evicted pods to other nodes. Graceful node shutdown enhances cluster reliability and minimizes the impact of node maintenance or failures on running applications. Pod priority-based graceful node shutdown. Pod priority-based graceful node shutdown ensures critical pods are gracefully evicted before a node shutdown. Kubernetes assigns priority levels to pods, with higher priority pods evicted first during node shutdown. This mechanism prioritizes critical workloads, ensuring they receive preferential treatment during cluster maintenance. Pod disruption budgets can be used to define constraints on pod evictions, ensuring critical pods are not evicted beyond a specified threshold. By gracefully evicting high-priority pods first, Kubernetes minimizes service disruptions and maintains application availability during node shutdowns. Non-graceful node shutdown. Non-graceful node shutdown handling in Kubernetes addresses scenarios like hardware failures or sudden power outages. Kubernetes detects node failures through missed heartbeats and takes corrective actions. It triggers rescheduling of affected pods to healthy nodes to maintain application availability. Persistent volumes may be used to ensure data integrity and avoid data loss during node failures. Non-graceful node shutdown handling enhances cluster resilience and minimizes downtime by quickly recovering from node failures. Swap memory management on nodes. Kubernetes recommends disabling swap usage on nodes to prevent performance degradation. Swap memory can impact pod performance by causing excessive swapping. Kubernetes monitors node resource usage, including swap memory, to ensure optimal performance. Disabling swap usage helps maintain predictable performance and avoids resource contention. Swap memory management is essential for optimizing containerized workloads and maintaining cluster stability in Kubernetes environments.